Example. Evaluate double integral on d 2x minus y dA, where d is the region bounded by the parabola x is equal to y square and the straight line x minus y is equal to 2. We draw the graphs. X-axis and y-axis. X is equal to y square. This is parabola. This is y is equal to plus x and y is minus 6. And this is the line. X is equal to 0 minus 2 and x in 2. So this is y is equal to x minus 2. D viewed as a y simple region. Do you remember y simple region? This is, we view parallel line on y-axis, parallel line, this is D, and x, y, y is plus x, y is minus x, and this is y is x minus 2, and we write this type x is equal to y square. X is equal to y square, and x is equal to y plus 2. Area is the same, but this time D viewed as a x simple region. X simple region. Area, this area. D viewed as a x simple region. the region D is both y simple and x simple. This point is important. If we these equations equal, this point is 4, 2. This point 1 minus 1, 1 minus 1, 4, 2. And this point is 4 and 0, and this point is minus 1 and 2. Okay. Firstly, we choose this, and viewing D as a y simple region and using Fubini's theorem, we want to this double integral on D to x minus y dA, and first, please attention, this is if you want to this integral, we divided two area, because this area lower boundary and upper boundary, and this area lower boundary and upper boundary as a y simple region. This point is 1, so x is from 0 to 1, and y is lower boundary is minus x, upper boundary is plus x square x, 2x minus y dy dx, plus now and this area from 1 to 4, 2x minus y, upper boundary and lower boundary. Lower boundary is y is x minus 2, and upper boundary is roots x dy dx. The reason is that the lower boundary of the change at the point 1 minus 1 from y is minus x on the left to y is x minus 2 on the right. In other words, the lower boundaries of D consist of two curves when viewed as a y simple region, and then is equal to 0 to 1 integrated this term for y 2xy minus y squared divided 2 and minus roots x and plus roots x dx, and then from 1 to 4 integrated 4y 2xy minus y squared 2, and then lower boundary is x minus 2, upper boundary is root 6 dx, and then from to 0 1, and we write on the y on x and then minus this term 2x minus minus plus and minus minus is 0 x and 1 4 plus 2 minus x minus 1 divided 2 x minus x minus 2 square dx. And then you are calculate this term. A bit hard and long integrated. On the other hand, viewing d as an x simple region, we have double integral on d 2x minus y dA is equal to, please, minus 1 and 2. Upper boundary is this and lower boundary is this. So minus 1 to 2 and lower boundary is y square, upper boundary is y plus 2. Just only one area. 2x minus y dx dy is equal to x square minus xy from to y square to y plus 2 dy, and then minus 1 to 2 y plus 2 square minus y fourth minus y plus 2 minus 2 dy, and is equal to from minus 1 to 2 4 plus 2y plus y square, sorry, y third minus y fourth dy. And then you calculate easily for y plus y square plus y fourth divided 4 minus y 5 divided 5 and from -1 to 2. Calculate 243 divided 20. This example shows that it is sometimes easier to integrate in one order rather than the other due to the shape of D. Therefore, we prefer to view D as viewed X simple region. If you choose this a very hard way. Now, if we had expressed D as a y-simple region, we would have involved much more work for the same results. The choice of the order of integration may be influenced also by the nature of the function fxy. It may be impossible to compute a given iterated integral, but easy to do so after we reverse the order of integration. In other words, the nature of the function dictates the order of integration, as the next example shows. Example: evaluate from 0 to 2 y divided 2 to 1. Y, example, exponential x third dx dy. If we try to evaluate the integral as it stands, we are faced with the task of first evaluation for dx. Integral y exponential x third dx. But it cannot be expressed in terms of elementary functions. So we try to evaluate the integral by reversing the order of integration. The order of integration of the given integral suggests that the integration region D is xy, so 0 is equal smaller than y is equal smaller than 2, y divided 2 is equal smaller than x is equal smaller than 1. We sketch the region D. Region D is, we sketch x, y is 1, this is x is equal to y divided 2, this point is 1, 2, this region. Then, from this figure, we see that an alternative description of D is xy, so 0 is smaller than x is equal smaller than 1, and 0 is equal smaller than y is equal smaller than 2x. This line same times y is equal to 2x. And this enables us to express the double integral as an iterated integral in the reverse order. Now, from 0 to 2 and from 2 y divided 2 and 1, y exponential x third dx dy. Now we calculate first this term from 0 to 1 and from 0 and to x. Now y exponential x third dy dx. Please attention to this. And is equal. Now we integrated this integral and from to 0 to 1 divided 2 y square exponential x third from 0 to x, and from the 0 to 1 divided 2x square exponential x third dx, and from to 0 to 1 2x square exponential x cubed dx. We say u is equal to x cubed, du is equal to 3x square dx. So is equal to u is 0 and u is 1, 2 du divided 3 and exponential and 2 divided 3 exponential u from 0 to 1 and 2 divided 3 exponential minus 1 is equal to 1.14. We calculate. Another example. Integration area, this area. This is d1 and d2. D is d1 plus d2. This is xy is equal to 16 and y is equal to x, and for 0.8 0 point and 0.4 point. This is area. Integration. Evaluate. Double integral on d x dA over the region D. The region D is not simple in the x direction. This is because all horizontal arrows doesn't lie in the region D. To evaluate this integral, we need to view D as y simple region, vertically simple. This is simple. D1 is x, y, so from 0 is smaller than x is smaller than 4, and y is lower boundary is 0, upper boundary is x, and D2 x, y, so from 4 y, and from 4 to 8, and lower boundary is 0, upper boundary is y is 16 divided x, 16 divided x. D is D1, D2. D and D2, D1 and D2 are the y simple regions. Using Fubini's theorem, we obtain double integral on D x dA is equal to D1 x dA dx plus D2 x dy dx, and then x is from 0 to 4, y is from 0 and x dy dx, and plus x, sorry, this is x, sorry, this is x from 4 to 8, and x is from 4 and 8, y is from 0 and 16 divided x, and x dy dx, and is equal to 0 to 4 integration for y, so xy, y is 0 to x dx plus 4 to 8 integration to 4y, xy, y is equal to 0 to 16 divided x dx, and then 0 to 4 x square dx plus 4 to 8 x product 16 divided x dx, so is equal to x cubed divided 3 from 0 to 4 plus 16x from 4 to 8, and is equal to 256 divided 3. This is solution.